Hello everyone, welcome to 𝐿ustraca. So in this lecture, we are going to learn about the limiting depth of neutral axis of a RCC section in Flexure. So in this explanation, the basis of will be IS456 2000. So whatever I'll be explaining here, it will be based on the considerations in IS456 2000. Okay, so let's get started. So let me just, as I'm talking about the RCC section in Flexure, so let me draw a RCC section. So let us consider it as a beam, right? So here, suppose we have a beam, and let me draw a line. I will come to this, you can say, concept of neutral axis. First of all, let me draw it. So all of us have already studied this, so I'm just giving a brief of this. So here you can see we have a line, and I am writing it now as the neutral axis. Okay, so suppose this is the width of the section, which is, suppose we consider it as B. Okay, and this is the overall depth, which is D. Fine. Now what we know, that whenever if we apply any load on the beam, okay, what will happen? The beam will bend. So as it is in Flexure, suppose it will bend like this. If we consider the beam like this, suppose, right, the load is applied here, the beam will bend like this. So the top, if you see this line, I have drawn a line, so there will be a zone where all the strips, or you can say all the fibers of this particular zone, will be under compression, right? Suppose this area, so it will be under compression, and the bottom zone, this zone, the green one, will be, so all the strips present in this zone will be under tension. So it will be under tension, and this zone will be under compression. And the line which is dividing these two, zones, or you can say two zones of compression and tension, this line we call it as neutral axis. Okay, fine. So some fibers of the section here, some fibers of the section will be under compression, and some fiber of the section will be under tension. And the fibers under compression and the fibers under tension is divided by a line, you can say imaginary line, which is called as neutral axis. So this is the basics we all know. So that means we are considering that this zone is under compression and this zone is under tension. Okay, now what is the assumptions that we make in IS456? That the concrete is good enough to take the compression, but we do not consider the concrete to be effective under tension. So what we say, that whatever tension we are getting here, obviously we know concrete is weak under tension, so the tension will be taken by the reinforcement bars or rebars, right? So that means we will be providing some reinforcement bars here. Okay, though the concrete 10% of the compressive strength of the concrete it will be considered as the tensile strength of concrete, but here the assumption is made like that the whole tension will be taken by the steel itself. That means the reinforcement bar you are providing, it will be taking the hold you can say tension, right? So that means the if you draw the effective depth, so in that case the centroid of these bars, so from the top fiber here I'm considering the beam as a simply supported, or suppose a section which is at the mid section. If it is a fixed beam, obviously the top fibers will be under tension and the bottom fibers will be under compression, so the vice versa will be happen. You just understand the concept that here the effective depth, now how much it will be. So if I just take this line, so the effective depth will be this, it will be my effective depth small d. Okay, so it is my effective depth. Fine. Okay, so now if we draw the strain diagram of this section, these fibers in this zone are under compression and the steel or this zone is under tension, which tension is taken by the steel itself. Okay, so these are the area of the steel that we are providing. It is nothing but the AST. Okay, area of steel under tension. Fine. So now if we draw the you can say strain diagram, so how it will be. So from here and this. Okay, so I'll draw a line. Okay, so this will be compression, it will be the tensile strain. Fine, so this is my strain diagram. So this is my tensile strain area and this is my compressive strain. So now the maximum compressive strain taken by the concrete, okay, at the, or you can say the maximum strain at the outermost fiber of the section. So here at this particular zone, so the maximum compressive strain will be how much? Maximum compressive strain will be how much? So the maximum compressive strain, we all know it is 0.0035. Maximum compression that will be taken by the concrete. Okay, and the maximum tensile strain in rebar, or you can say in steel, how much it will be? So it will be 0.002 plus 0.87 Fy by Es. Okay, we all know this from where? Let me show you. As we are referring IS456, so you can see, you can have a look on IS456 also. So this is the stress strain diagram. You can see corresponding to the maximum strain of 0.0035, we will be reaching the FCK. That is the I can say strength of compressive strength of concrete. The maximum value will be reaching here. So here it is written that the maximum strain in concrete at outermost compression fiber is taken as 0.0035 in bending. Okay, so we are talking about bending. And if you talk about the steel, the tension, so you can see the maximum strain in tension reinforcement in the section at failure, that means the maximum one, okay, shall not be less than Fy by 1.15 ES plus 0.002. So if you just do this 1 by 1.15, so it is basically 0.87. Okay, so that means we are getting 0.87 Fy by Es plus 0.002. Right, so this is what we have written here. This is what we have written here. Okay, so now what is this neutral axis? You can say maximum neutral axis depth, or you can say limiting depth of neutral axis. So when the concrete reached its maximum compressive strain of 0.0035, and when the steel simultaneously reached its maximum tensile strain of 0.002 plus 0.87 Fy by Es, then the depth of this neutral axis at this condition, when both the concrete and steel has reached their maximum strain limit, so in that case the depth of the neutral axis, sorry, Control Z, okay, so in that case the depth of neutral axis, we call it as this depth, okay, we call it as this depth, we call it as XU limit or XU max. Also in some books or in the code it will be written as XU max, maximum depth of neutral axis, maximum allowable depth of neutral axis. So you can say XU limiting equal to, you can also write it as XU max. Okay, so the limiting depth of neutral axis or the maximum depth of neutral axis. Now what will happen? What will happen if it is less, or like it is greater than this, or it is less than this? So when the concrete at the top of this neutral axis and the steel at the bottom of this neutral axis reaching their maximum compressive strain and maximum tensile strain simultaneously, in that case the section that we have taken, it is known as a balance section, right? So in that case, if we just consider that suppose the steel is reaching its maximum tensile strain before the concrete reach its maximum compressive strain, so what will happen? The section under tension will fail before the concrete fails. That means the steel will fail before the concrete fails, right? So that is called a under reinforced section. That is called a under reinforced section. So there, in that case, the neutral axis will be above here somewhere. It will not be at the XU max position, it will be above here. So that means the strain in the steel will be higher than the strain in the concrete at a particular you can say period. Okay, that means the strain in steel will reach its maximum limit before the concrete reaches its maximum strain limit. Now we can also think about the opposite, that if the concrete reaches its maximum strain 0.0035 before the steel reaches its you can say maximum tensile strain of 0.002 plus 0.87 Fy by Es. So in that case the neutral axis will be here. Okay, so that means the strain in concrete will be higher than the strain in steel, and the concrete will fail before the steel fails. Okay, so in that case we call that condition as over reinforced, because we have provided that much amount of steel here that the steel is not at all reaching its maximum limit, but before that the concrete is reaching its maximum limit. So if the concrete fails, that failure will be of brittle type, and if the steel fails before, as the steel is a ductile material, so in that case that failure will be of ductile type failure, right? So we always want a failure mode to be a ductile type of failure, so we prefer providing a, you can say, singly reinforced section, right? Or under reinforced section. I would say under reinforced section, not over reinforced section. So now when this is in the limiting condition, so it is a balance section. So this is a different condition. Now what we need to find, that how will we be finding this limiting depth for particular section, okay, or for concrete section under flexure. So if you see that if this is my XU limit and this depth, this whole depth is my effective depth D, then how much will be this? How much will be this? How much will be this? So this will be my D minus XU limit, right? D minus XU limit. right? Okay, so now you can see we have two triangles here. Let me just name those. So suppose A, B, C, okay, and D, B, E. So we have two triangles, triangle A, B, C, and triangle E, B, D. So these are similar triangles. Similar triangles, right? So if these are similar triangles, then what we can write? That we can write that AC, you can see here. Let me change the color from red to different colors. Let me take it as black itself. So we can write AC, this AC by AB will be equal to ED. You can see AC and ED. So ED by BE, right? So if we put the values here, so AC is nothing but 0.0035 by AB. AB is nothing but XU limit, right, equal to ED is nothing but 0.002 plus 0.87 FY by ES divided by BE. BE is nothing but D minus XU limit. Okay, you understood this? From the similar triangle we have got this equation. Now we can easily solve it and we can find the XU limit. So if you just solve it, if you see what we'll be doing, suppose we'll be doing the cross multiplication. So we'll be taking this D minus XU limit at the top. So D minus XU limiting by XU limiting equal to 0.002 plus 0.87 FY by ES divided by 0.0035. Okay, fine. Now we can break it down. So it will be D by XU limit minus XU limit by XU limit equal to how much it will be? So you can just do it. So it will be 0.002 ES. We are doing this, okay, we are just adding it. So 0.002 ES plus 0.87 FY, then ES will be coming down, so 0.0035 ES. Fine. So now if we just see that this and this will get cancelled and we will be having 1 here, right? We'll be having 1 here. Now if we take this 1 here in this side, in the right hand side, so how much we'll be getting? So if we just write D by XU limit equal to, we are taking this 1 in this side. Okay, so how much we'll be having? It will be 0.002 ES plus 0.87 FY by 0.0035 ES. It was -1, so it will be now +1. Okay, fine. So you can just Now it is a simple calculation, just we have to solve, that's it. So if I just do it, it will be 0.0035 ES, and it will be 0.002 ES plus 0.87 FY plus, now multiplied by 1, so it will be 0.0035 ES. Okay, now you can see we have two terms. This 0.002 ES and 0.0035 ES. So if we just add it, how much we will be getting? So let me just check. 0.0035 plus 0.002. Okay, so it will be 0.0055. Okay, you can see 5.5 multiplied by 10 power minus 3. So 1, 2, 3. Okay, so it will be 0.0055 ES plus 0.87 FY by 0.0035 into ES. Okay, now we can put, so now we can write, I can say replacing or just write placing ES equal to, we know Young's modulus of, you can say steel rebar, so it will be 2 into 10 power 5, right? Okay, so how much we will be getting? D by XU limit will be, let me write it properly. So D by XU limit equal to 0.0055 multiplied by 2 multiplied by 10 power 5 plus 0.87 FY divided by 0.0035 multiplied by 2 multiplied by 10 power 5. Okay, so how much we will be getting here? So you can just do it easily. 0.0055 multiplied by 2 multiplied by 10 power 5. So we are getting 1100 plus 0.87 FY, and here if we just write 0.0035 multiplied by 2 multiplied by 10 power 5, so it will be 700. Okay, now we can easily find the XU limit if you just reverse it. Okay, if you just reverse it, so it will be XU limit by D equal to 700 by 1100 plus 0.87 FY. So how much will be XU limit? So my XU limit will be 700 by 1100 plus 0.87 FY multiplied by my effective depth. Fine. So this is the, you can say, equation that will be solving to find out the neutral axis, you can say maximum neutral axis depth or limiting depth of neutral axis. In that case, what we need the, you can say, grade of steel and effective depth, right? So now in general, suppose we have grade of steel, so I'll just write grade of steel. So suppose we have, let me change the color, so we have Fe Fe215, right? 250, sorry, Fe250, not 215, 415 and 2. Okay, so Fe250, what is the Fy value? So it is 250 Newton per mm square, right? So in that case, what will be my, I'll just write it here, what will be my XU limit? So XU limit will be 700 by 1100 plus 0.87 multiplied by 250 multiplied by D equal to, let us solve it. Let me take it in this side. So it will be 700 divided by 1100 plus 0.87 into 250. So how much we are getting? We are getting a value of 0.53 D. This is for Fe250. Okay, now if we do same for Fe415, so the Fy is equal to 415 Newton per mm square. So the XU limit will be how much? We just have to replace this. We just have to replace this here, right, by 415. So if I just do it here, so 415, we are getting a value of 0.479 D, which will be equal to 0.48 D. Okay, now similarly if we do for Fe500 grid, so these grids are mostly used, so that's why I'm writing like this. Fy will be 500 Newton per mm square. So in that case, XU limit will be, again we'll be replacing it by 500. So we'll be replacing this by 500. So it will be equal to 0.456. Okay, so let me draw with this 0.456 D, which will be equal to 0.46 D, right? So now whatever steel grade you have, depending on that, you can find out the limiting depth of neutral axis. So what will happen if the limiting depth crosses this particular value? In that case, what will happen? It will lead to brittle failure. That means the section is over reinforced and it will lead to brittle failure. If the neutral axis, the depth is less than that, then the section is under reinforced, which is desirable, that the steel should fail first. Then we will have time, or we will have warning, as the steel is a ductile material, right? So now if I just take you to you can say our code IS456 2000 and page number, I can say 70, you can see it is clearly written these values, that for Fy equal to 250, the neutral axis depth, you can say XU max by D that they have written. Okay, so you can just, if you multiply with this D, then we'll be getting the same value, right? So XU max by D equal to this, so XU max equal to D cross multiply. Okay, right? So we are getting 0.53 for 250, 0.48 for 415, 0.46 for 500. Similarly, you can do the same for other grade of steels also. Okay, so I hope it is clear how we have these values are you can say given here. Okay, a very pretty simple calculation is done, and then these you can say values are worked out. So I hope this thing is very I can say clear to all of you, how we can calculate the limiting depth of neutral axis for any I can say concrete RCC concrete section under Flexure. Fine. So if you have any doubt, you can always write me in the chat box. And for such updates on my channel, please do subscribe my channel if you are not a subscriber. And I will see you in the next video. Thank you.